And there is, oh, sorry.
It's okay, now it's good.
Thank you. And clearly there is two obvious kind of class, some kind of tautological classification, that is the one containing periodic orbits. On the one without it. So that is tautological. That will be called aperiodic classes. We cannot assume that all the classes contain periodic orbits, even for analytic algebraic dynamical system. We have seen that in the NO families, for generic parameters, we have uncountably many chain recurrent classes. But in general, we only have countably many periodic orbits, because generically the dynamic is a Kupka-Smelch, that is, every periodic orbit is hyperbolic, so isolated. And if you take the period, so you have only countably many. So many times you have uncountably many aperiodic classes. Nevertheless, clearly the most important for understanding, for making the structure of the dynamic, are the one with periodic orbits. So, okay, they can be complicated. And now I will try to see if some generic assumption allow us to understand better these chain recurrent classes. So we will make some generic assumption on the diffeomorphism in order to understand better the classes.
If you have a shadowing, then it doesn't help, because shadowing orbits might be independent classes.
So shadowing,
if you have shadowing,
you have only in some hyperbolic setting,
but still,
so it certainly can help. So the one which are most understood are the one with periodic orbits. But with periodic orbits, we compete with, the chain recurrent classes compete with another canonical set associated to it. So if you have periodic orbit, so let's consider classes of periodic orbit. Most of the time, I think all the time, I will consider only hyperbolic periodic orbit. As I will take some generic assumption, my diffeomorphism will be Kupka-Smelch in general, so every periodic orbit are hyperbolic. Okay. So we have another classical set associated to, so you have P periodic saddle. So the first important set associated to a periodic saddle has not been the chain recurrent class, but the one defined by Smelch. So let me recall quickly. So consider the set, you have F, a diffeomorphism, string diffeomorphism. Of a compact manifold. So consider all the X periodic point, periodic orbit, let's say gamma periodic orbit. On this set, Smelch defined an order on that set. You will, let's say for the moment, a pre-order. Let's say that gamma is less than sigma if the unstable manifold of sigma have a non-empty transverse intersection, so that means transverse intersection, with the stable manifold of gamma. Okay, so I say preorder because that is reflexive and transitive. So this relation is transitive, that is the lambda lemma. If you have a saddle whose unstable manifold is cutting transversally at some point the stable manifold of another saddle, so let's say gamma here, sigma is there, and delta now there, and you have a third saddle, so that the unstable manifold of sigma is cutting the stable manifold of delta. Then, by the lambda lemma and by the transversality here, this one is intersecting on this on the whole unstable manifold. So at some moment it will cut this one, so you get the transitivity. So this relation is reflexive is trivially reflexive because the stable manifold intersect at the point. So now if you if you symmetrize it, so you will say that gamma is homoclinically equivalent to sigma if, so gamma is less than sigma, and reciprocally sigma less than gamma, and that is an equivalence relation. So this implies the fact that we require transversality implies that in fact the dimension of the stable manifold are the same. Okay, and so we can define the homoclinic class of gamma as the closure of the sigma, which are equivalent to gamma. And there is, I can put theorem because it's not something which is trivial, but it's well known that you can make another expression for gamma, which is, it is the closure of the transverse intersection of the stable manifold of the I put gamma for telling orbit and not point. So you take the stable manifold of the orbit, you consider all the intersection with the unstable manifold of that orbit, and you take the closure that is the same as the closure of the periodic orbit, which are homoclinically related with with gamma. In one direction, it is the fact that this one is that IH of gamma is included there. That is easy because each time you have that is just the lambda lemma. Once again, you have two saddles which are homoclinically related. Then this one by the lambda lemma accumulates there. So this one accumulates there. So this point is accumulated by the transverse intersection point of my saddle. So we have this inclusion of this one there. In the other direction, it is deeper, and in some sense, it's the beginning of the hyperbolic theory, because and it's something I think, which is the good understanding of the Poincaré discovery of the transverse homoclinic intersection, is that each time you have a transverse intersection of a saddle, so close to there, you can build a small horseshoe. And this horseshoe have a local dynamic for some large iterate of F. So is this horseshoe, so that is not the first iterate. You have this rectangle, its image will be some rectangle like that, its second image like that, and after a long time, you will cut again, making this horseshoe. So this long return time will contain a full shift. On full shift may density of periodic orbits, each homoclinic correlated with gamma, and you get the other intersection. So that is in fact, I think we use, everybody dealing with diffeomorphism, deal with homoclinic class with this equality as it was a triviality, but okay, that is something deep in fact.
So just to clarify,
Yep.
you're looking at the accumulation set of the intersection points, or
Yes.
I thought that they
So here
should just contain
you
periodic.
consider. Sorry, I forget this one. So the homoclinic class, by definition, is a closure of the class for the homoclinic relation. And this closure coincides with the closure of the transverse intersection point of the stable manifold with the unstable manifold of the point. So this equality makes why this set is so important. And one direction is mostly easy and is what is called the lambda lemma. The other is deeper, is the fact that any homoclinic intersection leads to some horseshoe for some power of your dynamic. Okay? So this homoclinic class is, so H of gamma is transitive. Donc compact, invariant. And in the case of axiom A, that is how Smale builds his basic pieces of the spectral decomposition. So I start the course recalling that Smale split the axiom A dynamics in pieces, and that are the pieces. You consider all the periodic orbits, you take the equivalence relation, you take the closure of them, you have finitely many disjunct transitive invariant set, and in the case there is no cycle, they are separated by the filtration. So that was Smale's theorem. Okay, so that is an important set associated to periodic orbit. And clearly, we have, so remark, that the homoclinic class of gamma is contained in the chain recurrent class of gamma always. Why is that? If you take any intersection of the stable and unstable manifold, not necessarily transverse, but transverse if you want, of some orbit gamma, from that point, which is an even non-transverse intersection point, you can go from this point to gamma, and you can go from gamma to that point by pseudo-orbits. So certainly, they are included. Are they always the same? Certainly not. It's not. There is two notions. So I will give you an exercise that I will not do for showing that that can be truly different. So the exercise is a little bit artificial, but okay. It's just for thinking. So for those who know, for the other, I will say that it is not so important, so I will explain why. So exercise. Consider X on R3 having a Lorentz attractor, a flow, so vector field, a Lorentz attractor, so very fast. You have a saddle point with a weak stable, a strong stable, and if you take some transversal, so when you pass the corner, you arrive to some cuspidal region. And for being an attractor, always going away, you want to send it back inside. So you send it back inside. And you got what is called the Lorentz attractor. So you need some expansion and so on. So let's call this saddle sigma. And also, I want you to take as diffeomorphism F is the time one map of X. And compare H of sigma. Sigma is certainly an hyperbolic fixed point for F, and C of sigma. Okay, I think that can show you that it can be different. If you don't know, you have no idea what it is, the Lorentz attractor, so just notice that sigma is an hyperbolic saddle of vector field. On that, the Lorentz attractor, I will call it lambda. Lambda is a transitive invariant compact set. So just take that, and with that you have to be able to make the exercise, even if you have no idea what is Lorentz attractor. Okay, so, but here the situation is not at all generic. To be the time one of a flow is not a generic situation. So let's see if putting some generic assumption may help. It may help because in particular of that proposition. So let's assume that you have that F associated to a periodic point PF. So PF is an hyperbolic saddle, hyperbolic saddle fixed point, saddle periodic point. And I assume that so it varies continuously with F. For the C1 topology or CR topology are larger than 1. Okay, so we have a given fixed point, so you can consider the map which has F associated the homoclinic class of PF and F associated the chain recurrent class of PF. Does they vary continuously? The answer is no. These sets do not vary continuously. But there are some regularity, and they are in the inverse direction. So this one is lower semi-continuous, so I look at this map in the set of compact, let's say set of M, a set of compact set, subset of compact set, with the Hausdorff topology. Okay. So this map is lower semi-continuous, and this one is upper semi-continuous. So these two notions, which are very old, has been very popular in the starting of the 2000 because we use it a lot at this moment. But at this moment, I just discovered them. I had no idea what meaning to be lower semi-continuous for a map to for a function associated a compact set and reciprocally. So I'm not assuming that everybody managed these two notions with fluently. So let me tell you what it means. And I will make the proof, which is very easy. So what it means that there exists, for given any f, there exists a neighborhood, or the f for C1 neighborhood. I can put CR, but C1 is bigger, so C1 contains CR neighborhood. So that for any okay, I forget to put any epsilon. For any f, any epsilon positive, there exists a neighborhood which depends on f on epsilon, so that if G belongs to O, then, okay, what I want is that, what I claim here is that the homoclinic class of P for G cannot be too small with respect to the homoclinic class of P for F. So for expressing that, I will say that the class of PF is included in the epsilon neighborhood of the class of PG. So in some sense, this says that this class is not too small with respect to this one. Okay. And at the contrary, or the other, is that the class of the chain recurrent class of PG is contained in a small neighborhood, so an epsilon neighborhood, of the chain recurrent class of PF. Given F, if I make small perturbation, this one may become much bigger, but cannot become much smaller, and this one is the contrary. Okay.
One cannot explode, one cannot implode.
Yes. In some sense, it's something like that. Okay, what's the proof? Well, that is, you just have to consider the, for example, HFPF is a closure of the transverse intersection between the stable manifold of PF and the unstable manifold of PF. Okay? So here you have your point PF, and you look at the transverse intersection between the stable and unstable manifold. Okay? And you consider this set, and so that are countably many points, and you take the closure, but as it is countably many points, if you take a large enough set of points, so you take all these that I draw here, you will get that, so you take finitely many intersection points xi, which are transverse intersection of PF and the unstable manifold of PF. Okay, so that you have that the class H of PF is contained in the epsilon subret 2 neighborhood over 2 neighborhood of this set xi. this finite set. But now, as the intersection is transversal, if I change a little bit the manifold, the point vary continuously. So each of these points is varying continuously. You have finitely many points. Your point here vary continuously. The stable or unstable manifold vary continuously, making that point vary continuously. So for G close to this one, this set remains almost the same and contain in its epsilon neighborhood the whole set. Okay.
The same works for not implosion for Julia's.
Sorry?
The same works for not implosion of Julia's.
Of Julia's set.
You have periodic points approximated in the move on the slide.
Yes, if
the same.
Yes. So if I wanted to deal with the periodic orbit, I could also taking care of choosing finitely many heteroclinic intersection points for being sure that the connection remains. Because it's not enough that the point survives. We need that the connection survives.
Here.
For my case, yes. For homoclinic classes, yes. For the Julia set, you don't deal with homoclinic intersection. For the other is a specific things that I explained very quickly yesterday.
It's here because neighborhood of one periodic trajectory is growing, covering, jumping, so that covering also.
Ah, yes, so you all.
And vice versa. It's the same, but
Okay.
dimension one. You consider trajectories, not just.
So if you have a chain recurrent class, yesterday I explained that every chain recurrent class, you have C a class, it admits a basis of neighborhood which are filtrating neighborhood. So I try to recall what are filtrating neighborhood. So you have some attracting region here, and some repelling region, but which intersect on the filtrating region is the intersection.
What you are proving
On,
what you are discussing.
I am trying to show
That's the second.
the second one.
Which for Julia is not correct. Julia can explode.
So this one can explode, this one cannot. So that the bigger can be smaller, and the smaller can be bigger.
This is
Okay. So you have this region. On this region, if you change f by g close, even C0 close, the attracting region remains an attracting region, the repelling region remains a repelling region. So the filtrating region remains the same. And the good thing of a filtrating region is that pseudo-orbit which touch a filtrating region is completely contained in it. So the chain recurrent class are contained in filtrating region and they cannot be half in and half out. So you have these which make a barrier. It's a basis of neighborhood, so you can choose one in this neighborhood. You can have a filtrating region of PF in the epsilon neighborhood. And now when you make G vary, your point PF is changing a little bit in PG. But as that is a filtrating region, its class needs to remain in the filtrating region.
okay. So let me comment for complex situation for polynomials. Julia set cannot explode, but
Yes.
fill it in Julia set cannot explode because it is complement of basin of attraction.
So maybe
So it's precisely the same.
it's very possible that it is precisely the same.
Precisely, but
No, it's up
type
to.
of situation is the same.
We have to see if, considering the non-injective case, the chain recurrent class is the full Julia. It's very possible that it is the full Julia.
Yeah, but I say now about fill it in Julia set, which is complicated structure including some bases, etc. But
Okay.
it's complement of basin to infinity. And this cannot explode this complement because what was escaping to infinity still escapes to infinity, up to close to the boundary.
And so what is the interest of having a semi-continuity? So if you remember the small classes, we have already seen this kind of notion, but on R. But it happens that it is the same when you look at function from in value to the set of compact set. That is, when you have some semi-continuous function, it is generically continuous. So as a corollary, for f C1, C are generic in any, for R larger or equal to 1, including infinity, you have that f associated to the homoclinic class of Pf, or f associated to the chain recurrent class of Pf are continuous map. Maybe I have to say that the first we truly used this notion deeply has been Flavio Abdenur. It was known before, but he used that and make that we understood that it was an interesting property. So now there is, I want to present the main tool which makes that we will be able to understand the chain recurrent classes. I will give it in a simple version. Okay, so this theorem, let's say that it starts with Hayashi. You have to put as a name Lanwen, Marie-Claude Arnaud. On the final version, I think I didn't see. I forget. If I remember the name after, I will say put again. And then myself with Provisier. So we start with F, which has, so that every periodic point is hyperbolic. Well, in the case of conservative, we can also deal with elliptic points. Or if you take, so PF saddle periodic, saddle, so an hyperbolic periodic saddle, and you take any point in its chain recurrent class, then there exists G, which is C1 close to F, so that H belongs to the transverse intersection of PG, of the stable manifold and unstable manifold of PG. So that is what is called a connecting lemma. In fact, we can do more than that, but that is enough complicated for setting like that. Let me explain a little bit what's the subject. So